Hello, we're going to introduce direct current circuits. We're going to begin today by talking about a series circuit. So the key to a series circuit is that there is one path. There's only one path that the current can take, so we call it a series circuit. Before we can get into analyzing the circuit, we need to go over the rules for the circuit. So there's rules for voltage, current, and resistance. In order to correctly analyze circuits, you're going to need to know these rules, and we'll be talking in a few minutes about an effective way for you to keep them straight. So first, voltage. In a series circuit, voltage adds. That means that the total voltage drop across the entire circuit is equal to the voltage drop across the first resistor plus the voltage drop across the second resistor, and so on for however many resistors that we have. The rule for current in a series circuit is that current is constant. That means that the current, remember we use I to represent current, total current coming through the power supply has to be the same as the current that passes through resistor 1, as the current that passes through the resistor 2, and so on for however many resistors that we have. Resistance. The rule for resistance is that resistance adds in a series circuit. That means that the resistance of the total circuit is equal to the resistance of resistor 1 plus the resistance of resistor 2 plus the resistance of all other resistors added together. So those are the rules for series circuits. Now, I had mentioned that we would come up with an easy way or mnemonic to keep the rules straight. So the way that we do that is this mnemonic: Vir, Saka, Pakara. Let's write out what that means. V, I, R, Vir, voltage, current, and resistance. Saka, in a series circuit, voltage adds, current is constant, and resistance adds. So Vir, Saka, and I'll tell you the second part, which doesn't yet apply but will in a few moments, Pakara. In a parallel circuit, voltage is constant, current adds, and resistance reciprocals add. So you may have heard people in the halls talking about Vir, Saka, Pakara. This is the mnemonic so that you know the rules for resistor circuits. This is a pretty effective strategy for keeping your rules straight as you analyze circuits in this unit. Go ahead and take a moment to review rules 1 through 6. I came up with a general strategy for analyzing circuits. So since this is the first circuit we're talking about, we're going to talk a little bit about each part. So first of all, the two parallel lines of unequal length represent the power supply. The longer line represents the positive end, the shorter line represents the negative end. Now in this particular problem, you can see in the VERP table below that we know that this is a 60-volt power supply. So that is the voltage that will be driving the current through this circuit. Now it says resistor 1 is 5 ohms, so I'm going to label that. And it says resistor 2 is 15 ohms, so I'm going to label that. So let's just go explain generally what would happen with this circuit. So we would expect the current to come out of the power supply. We would expect it to flow through resistor 1, flow through resistor 2, and then come back into the negative terminal of the power supply. So the zigzags above R1 and next to R2, that is the symbol for resistor. So the first thing that you are going to need to do in any circuit, whether it be series or parallel, is to determine the total resistance. Now we're looking at a series circuit, so we know that resistance adds. So to get my total resistance, I simply need to add the resistance of each resistor. So I have a 5 ohm resistor and a 15 ohm resistor, which will get me a total resistance of 20 ohms. Now, hopefully you realize that this table, the VERP table, is laid out in really a nice way, because we know that voltage is equal to current times resistance according to Ohm's law. That means that the first column should be equal to the product of the second and third columns. We also know that power is equal to current times voltage. The next step in the process is to figure out the total current. So we've determined that the total resistance is 20 ohms. We were given that the total voltage was 60 volts. And the way that we're going to figure out the total current is we're going to use Ohm's law. V equals IR. So I know that my I total is going to equal my V total divided by my R total. And so that's just going to be 60 divided by 20. And so I know my total is 3 amps. So I'm going to fill that in my chart below. So that means that this purple arrow has 3 amps coming out of the power supply. Do all 3 amps have to go through R1? They do, because this is a series circuit, so there's only one path. Do all 3 amps have to go through R2? In fact, they do, because there is only one path. So I know that the current is 3 amps in R1 and 3 amps in R2. Now that's consistent with the rules as we remember using Vir-Sacca-Picaro, because in a series circuit under current, we see that it is constant, meaning that is the same for each resistor. And so as you can see, resistor 1 and resistor 2 have the same 3 amps of current. We're going to continue filling out the verb table. So I know voltage is equal to current times resistance. So we have 3 amps times 5 ohms. So 3 times 5 is going to be 15 volts. For resistor 2, I know that I have 3 amps times 15 ohms for a total of 45 volts. Again, if we go back to the rules, what's the rule for voltage in a series circuit? And you will see that voltage adds, which means that if I add the voltage drop across resistor 1 to the voltage drop across resistor 2, I should end up with the total voltage. So 15 plus 45 does in fact give me 60. We can now go ahead and fill out the power column, which is just going to be current times voltage, or column 2 times column 1. So when I do that, I have 3 amps times 15 volts is going to be 45 watts. And 45 volts times 3 amps is 135 watts. When I add them up, so 45 plus 135, I get 180 watts. We're going to now check to see if this is correct. So the way that we check is something called the power check. And the power check means that when we add them up, so the 45 plus the 135 gives us 180, that should be the same result as if we were going to take the voltage total times the I total. And our voltage total was 60. Our current total was 3. And 60 times 3 is 180 watts. So you can see that we get 180 watts when we multiply, and we get 180 watts when we add. So this circuit and the work that we did does in fact pass the power check. So that indicates that we have completed this verb chart correctly. We can now move on to our second example of a series circuit. So I've gone ahead and I've labeled resistor 1, resistor 2, and resistor 3 using the information from the verb chart. And I've also labeled the voltage at the power supply as 60 volts as indicated under the total voltage. We're now ready to go ahead and analyze this circuit. So again, as we can see, this current has exactly one path. We come out of the power supply, we have to go through our 1, we have to go through our 2, and we have to go through our 3. And then we return to the negative side of the power supply. So we can go ahead and write Vir, Saka, Pakara, which is our mnemonic for indicating the rules of circuits. So since we have only done series circuits so far, we're really just looking at this first row. So for resistance in series, we can see that it adds. So just like the last problem, my total resistance is going to be the sum of resistor 1 plus resistor 2 plus resistor 3. So 2 plus 6 plus 12 is going to give me 20 ohms total. So again, my first step was finding my total resistance. My second step is going to be finding my total current. Recall the way the table is laid out. Voltage equals current times resistance, and power is equal to current times voltage. So I could take my 60 volt total and divide that by my 20 ohms of total resistance. And again, I'm going to get 3 amps. So this is the second example, I think, where we got 3 amps. Just to clarify, current is not always the same. It's really just going to depend on each individual circuit. The process, though, is the same. You're always going to divide total voltage divided by total resistance to get total current. Now that we know our total current is 3 amps, we know all 3 amps have to come out of the power supply. All 3 amps have to go through resistor 1. All 3 amps have to go through resistor 2. And all 3 amps have to go through resistor 3. So I can go ahead and fill that in my chart. So 3 amps must go through each resistor. Refer to the Vir-Sakapakara table and you will see again that current is constant. And that's what we found to be true here. We're now going to complete the chart using multiplication. So the I column times the R column should of course give us the voltage column. So 3 amps times 2 ohms should mean I lose 6 volts across resistor 1. 3 amps times 6 ohms means I should lose 18 volts across resistor 2. And 3 amps times 12 ohms means I should lose 36 volts across resistor 3. So you can check on your calculator. Go ahead and add 6 plus 18 plus 36. And I think you're going to find that you get 60 volts total, which is consistent with the rule for voltage in a series circuit that it adds. Now we're going to go ahead and fill out the power column. So recall that power is equal to current times voltage. So 3 times 6 is going to be 18 watts. 3 times 18 is 54 watts. And 36 times 3 is 108 watts. So if you go ahead and add 18 plus 54 plus 108, you get a total of 180 watts. So to complete the power check, we need to see if P total is equal to I total times V total. And we get I total is 3, V total is 60. So in fact, we do get 180. So we can see that this passes the power check, indicating that we have likely completed this VERP chart correctly. So there is one more series circuit that you should go ahead and practice on your own and make sure that you get it correct.